Okay, thanks, Ms. Muse. This is now Mrs. Suderman, and I'm going to be completing the rest of the problems for this review video. So we're on number 7. The heat Q required to raise the temperature of water varies jointly as the mass of the water and the amount of temperature change T, and Q equals 20,930 joules when the mass is 1 kilogram and the temperature is 5 degrees Celsius. So let's go ahead and start out by setting up our function, and we're just going to do the plain function before we've plugged anything in. So the first variable, remember that's what our y is, so we'll have Q equals, the heat is, and always put the K right after the equal sign, and it varies jointly as the mass and the amount of temperature change. So we'll have times M and then times T. Okay, so to figure out the variation of the constant of variation K, we're going to plug in for Q the 20,930. So we have 20,930 equals K times, it gave us a mass of 1 and a temperature of 5. So then to get K by itself, 1 times 5 is just 5. So if I divide both sides by 5, that should give me K. And so here when I divide this by 5, I'll get that K is equal to 4,186. So then whenever we want to write the variation equation, we take that K value, plug it back into that plain one we started with, and so we'll get Q equals, now we know that K is 4,186, and then we have M times T. And then finally, we have find the mass when the heat is required. Find the mass when the heat required is 8,372 joules and the temperature is 10 degrees. So all we're doing here is practicing using that equation we've just gotten, and so we'll plug in our information. So Q here is Q here, is the 8372. We know that K is 4186. We're looking for M, and the temperature is 10. So we need to get this M by itself. So we're going to divide by, so 4,186 times 10, extra 0. So if I divide both sides by that, I'll get that our mass is 0.2 kilograms. All right, let's check out number 8. Number 8, the volume V of a gas varies directly as the temperature T and inversely as the pressure P. A certain gas has a volume of 10 liters and a temperature of 300 kelvins and a pressure of 1.5 atmospheres. So what is the constant variation K? Well, let's go ahead and set up the plain equation first. So the first variable will be V. So I'll have V equals, always immediately put the K right next to it. And the temperature, so it varies directly as the temperature, so that means anything that is directly varying goes on the top or jointly. And then inversely as the pressure P, so anything that's inverse goes on the bottom. So now to figure out the constant of variation K, we plug in the information that they gave us. So it has a volume of 10. We're looking for K. It gave us a temperature of 300 and a pressure of 1.5. So 300 divided by 1.5, we'll end up with 10 equals K times 300 divided by 1.5 is 200. And then when I divide both sides by 200, I'll get that K is equal to 0.5. And so to write the variation equation, I just need to fill in the K for that plain equation we started with. So we have V equals 0.5 T over P. Oh no, don't be mad. This is 0.05. So then this is 0.05t. Sorry about that. Easy little mistake. Don't make that mistake on your test. But see, I caught it, so we're okay. Let's move on. Okay, so for this next section, we're going to use factoring or the graphing calculator to describe the holes, if there are any, in the graph and any vertical asymptotes, if there are any. Okay, so we'll have the vertical asymptote, and I just made a few notes over here. So vertical asymptotes are when you find the factors of the denominator and set them equal to 0 and figure out what x would be equal to, and that will give you your vertical asymptote. Holes in the graph are whenever factored, you take whatever cancels, set it equal to 0, and solve for x. And let me scroll down a little bit here. For the horizontal asymptotes, we have that Bobo-Botanide. Depending on who your teacher is, they may say Bobo-Botan-eats DC or whatever. But in our class, Mrs. Suderman's class, we had said Bobo-Botanide, which would be if it's bigger on bottom, then it's y equals 0. And by the way, these are again talking about the exponents. So if the exponents are bigger on bottom, then it's y equals 0. Bigger on top, there's no horizontal asymptote. And if equal, divide the leading coefficients. So let's use this information to do these three problems. Okay, so we have x minus 1 times x plus 8 over x squared plus x minus 2. So let's factor the bottom here. So we will get x plus 2 and x minus 1. And let's see whatever cancels here. So then now we have x plus 8 over x plus 2. Okay, so for the vertical asymptotes, remember that's when we look at the denominator and set it equal to 0. And you may wonder, which one do I look at? Well, you look at the one that is the new denominator. So for vertical asymptotes, you're looking at the new denominator. Okay. So if I have that x plus 2 and I set it equal to 0, and solve for x, I'll get x equals -2. So that is the vertical asymptote. So I'll have x equals -2. For the horizontal asymptote, that's the Bobo-Botanide. So we again will look at this new one. So we have x plus 8 over x plus 2, they have the same exponent, so then, because that's x to the first over x to the first. So whenever you have the same exponent, you need to divide the leading coefficients. So that would be y equals, because horizontal asymptotes are y equals, so this has a coefficient of 1, that has a coefficient of 1. So 1 divided by 1 is 1. And then for the holes in the graph, you're again going to use that the cancel part. So like I said over here, holes when factored, take whatever cancels, set it equal to 0, and solve for x. So this time what canceled was the x minus 1. So if I set that equal to 0 and solve for x, I'll get x equals 1. So there will be a hole in the graph at x equals 1. If you wanted to find the point for that, you take that x equals 1 and you plug it back into your new equation and solve. So if we're looking for the y value for this point, just in case you're wondering, so we'll have the 1 plus 8 over the 1 plus 2. So that's 9 divided by 3, and that equals 3. So that's actually going to be at the point 1, 3. All right, let's look at this next one, number 16. Let's do this again. So it's a good idea that we factor everything first. So this top thing is x minus 5 and x plus 1. This bottom thing has a greatest common factor of x, and then it's x squared minus 5. Oh, 25. But then that's a difference of 2 squared. So we have x times x minus 5 and x plus 5. So we're no longer looking at these two. Okay. So let's see if anything cancels, and it does. The x minus 5's cancel. So we're left with x plus 1 over x times x plus 5. So for the vertical asymptotes, we're going to look at the new denominator and look at each factor and what x value would make each factor 0. So if I have this as one of them, so I'd have x equals 0, and I'd have the x plus 5 equals 0. So I need to solve both of these for x. Well, the first one's already solved, so that one's good, but then the second one I need to subtract 5, so I have x equals negative 5. So I have two vertical asymptotes. I've got one at 0, and I've got one at negative 5. For the horizontal asymptote, that's the bobobotinide. So I look at my my new equation here, and I've got x plus 1 over x times x plus 5. It may be tempting to say, okay, well, these have the same coefficient, but don't forget that this thing, if I were to multiply it out, that's x squared plus 5x. So now when I compare my degree, I've got x to the first over an x squared. So that's bigger on the bottom, and whenever it's bigger on the bottom, it's y equals 0. So we don't have to do any other calculations there. The horizontal asymptote is y equals 0. And then for the holes in the graph, we go back and look at whatever we canceled out, and that was the x minus 5. So when I set that equal to 0, I'll get x equals 5. So the hole in the graph will be when x equals 5. But if I want to find the exact point, I take that 5 and plug it back into my new equation. So I'll have 5 plus 1 over 5 times 5 plus 5. 5 plus 1 is 6. This 5 plus 5 is 10. So 5 times 10 is 50. And then if I want to reduce this, if I divide both sides by 2, I'll end up with 5, and then 6 divided by 2 is 3, and 50 divided by 2 is 25. Alright, and one more example. We've got x squared minus 3x over 4x minus 12. So let's start out by factoring everything. This thing on top, our numerator, has a greatest common factor of x, so I'll have x times x minus 3. And then on the bottom, this has a greatest common factor of 4, so when I take out the 4, I'll have x minus 3. Well, the x minus 3 is canceled, and so I'll have x over 4. For the vertical asymptotes, I look at my new equation here, and I say what x value would make my denominator 0? Well, I don't have any x's in my denominator, so therefore I will not have any vertical asymptotes. For the horizontal asymptote, use the bobobotinide. So if it's bigger on bottom, y equals 0, bigger on top, there's no horizontal asymptotes. And if it's equal, we'll divide the leading coefficients. Well, you may be figuring out, okay, where is my exponent? Well, you can either see that there's an x on the top and there's not one on the bottom, and right away see that it must be bigger on the top since there's an x there and on the bottom there's not. But remember that this is the same thing as x to the 0, right? X to the 0 equals 1. Anything to the 0 power equals 1. So even looking at it this way, I can see that the exponent on top is bigger. So when it's bigger on the top, there's no horizontal asymptote. So we don't have a vertical or a horizontal asymptote. However, for the holes in the graph, we did cancel something out. So let's set that equal to 0 and solve. So we'll get x equals 3. So there'll be a hole in the graph at x equals 3. But for the exact point, we take that 3 and plug it back into our new equation, and we'll ignore that x to the 0 now. So we'll have 3 over 4. Easy enough, so I'll have the point 3 and 3 over 4. Alright, that's it. Hope this was clear, and you can check out the answer key posted on the teacher website. Hope you're having a good day, and good luck on your test. Bye.